Thank you, and thank you for the opportunity to participate in this lively exchange of ideas. I will talk about Tukey's two pillars of replicability, which are not known to be these, some recent evidence, the relationship of the stat wars to replicability issues, frequent test versus spacing in response to these pillars, and New England Journal of Medicine guidelines as a casualty of this war. Tukey's last published work is a puzzling from 2000, is a puzzling encyclopedic entry on multiple comparison. It opens with a statement that multiple comparison deals with a diversity of issues that tend to be important, difficult, and often as resolved, as we heard in the last talk. But then it details only two issues: the FDR approach in pairwise comparison, based on his own paper, and the random effects versus fixed effect analysis in analysis of variance. But what's that to do with multiple comparisons? I mean, this is a puzzling one. We didn't understand it when I wrote with Henry Brown an entry about Tukey's work in multiple comparison. We simply left it out. Then came my enlightenment, I can say, as I was involved in studies in the gene and behavior area. There was a paper by Crabb et al. In Science in '99 where it compared 12 measures across strains in 3 laboratories. And in spite of strict standardization, such as the one that was advocated by Lackens, and the fact that it was a significant overall result, the lab interaction with genotype was statistically significant. And the conclusion was that experiments characterizing mutants may yield results that are idiosyncratic to a particular laboratory, which is the problem of replicability. We thought that using our computational computation tool, we solved the problems, and we compared 17 measures between 8 imprint stains in 3 laboratories, 1 at Tel Aviv, 2 in the United States. And this is the results that we got using the analysis run by Crabb. So we have the 17 endpoints, like time away from the wall and so on. They were all highly significant, with a few ones that are not. But strangely enough, the strain times lab interaction was also highly significant in these results. Now, when we treated the laboratories in a mixed analysis, as if they were random, then we got this very different picture. And what you see, the green ones are the FDR significant ones at the 0.05. The 0.0029 was the only one for only one. So this was in spite of the interaction. What the mixed model does is takes, of course, increases the variability, the standard deviation to do with the comparison, and takes this into consideration if something significant. On top of that, that's great. Now, notice the laboratories were not a random sample, okay? But when recalling Mann's warning in behavioral genetics in transition, that jumping too soon to discoveries and present discoveries in this area, just as in psychology, raises the issue of replicability, then I understood that Tukey's entry is about replicability of discoveries. And he was addressing selective inference and the relevant variability. And in fact, his approach was that you should compromise in some sense. And I'll explain in what sense. Both in both areas, selective inference with fault discovery is some kind of compromise, and the relevant variabilities with mixed model, even though there is not a truly random sample, is also a compromise. The second problem, the relevant variability, is an old one, and nothing new has happened in it. But selective inference intensified in recent years due to the industrialization of the scientific process, and this is what I think created the replicability issues to surface. Just recently, we entered a study, experimental study. We took single lab experimental results involving comparisons between mouse strains, the original results from mouse phenotypic database. We carried similar experiments in 3 laboratories, in Jackson Laboratory, 2 laboratories in Israel, without standardization, without extra standardization. We used a random lab mixed model analysis to assess replicability of the original results. So if the result was significant, it was replicable. We don't know if it's true or not. We simply say it's replicable or not replicable. We estimated a parameter, which is the interaction variability divided by interaction within each lab. And we did it for each endpoint from the database from our experiments. And we used it to adjust the single lab results by inflating the standard deviation. 60% of the single lab rejected results were not replicable. But using the adjusted single lab rejected results, only 12% were non-replicable. This is still under review, but it can be found on the archive. Going back to Tukey's paper, we found this. I found this in the discussion, this statement that where it says that scientific knowledge and our experiments are on 2 sides of a wide river. If you do your experiment here and you analyze it using fixed analysis, then you do a step towards scientific knowledge, but it is very close to where you started. And there is a long way to go to scientific knowledge. But if you do your analysis using mixed model, then the island reached by statistical inference is much closer to the scientific bank of scientific knowledge. And if we look at the results that Sen presented about the multi-lab experiments, then you can see that the variability between the laboratories average is much larger than the variability within, and certainly the variability extremely small confidence interval that are visible for the general problem. What about selective inference? Selective inference is inference on the selected subset of the parameter that turned out to be of interest after viewing the data. And it's relevant to all statistical methods, and it's hurting replicability. Seriously. There are 2 types. There's out-of-study selection, which is not evident in the published work, the file drawer problems, the garden of 4-key paths, p-hacking, and so on and so forth. All know about it. Okay? All are widely discussed and addressed. The Open Science Initiative addresses them, and so on and so forth. But there is a second one there. There is in-study selection, which is evident in the published work. Okay? This is selection by the abstract, by the discussion, by tables, by figures, selection highlighting those passing the significance threshold, whether 0.05, 0.005, or twofold, selection by modeling. My point is that this selection is not banned. In complex research problems, in-study selection is unavoidable. It is essential. You can't simply, as was stated before, you can't simply throw the result at the reader and say, you pick them. It's the responsibility of the researcher to do that. Let me give one example of selection of significant one by the abstract group. Giovanici et al. 95 looked for a relationship between more than 100, actually 130 times of food intakes and the risk of prostate cancer. The abstract reports 3 marginal 95 confidence intervals, only for those relative risks whose confidence intervals do not cover 1. And then the news headlines came up with eat ketchup and pizza and tomatoes and avoid prostate cancer. Now, the reason I bring this old one is because of the second point here. And this is the many continuing experiments and studies that were done on that. And this is the original one, Guinavucci, and this is how slowly it converges to the conclusion that although the pooled RR for raw tomato consumption was nearly significant, this association has remained non-significant since 2000. And this was a meta-analysis by Roberts in 2017, and it's still studied and stated as such. The point is, any adjustment for multiplicity would have ruled out that the 3 original results were not statistically significant. So what error rates are being used in selective inference? I would like to demonstrate it using by an example that New England Journal of Medicine editorial used to demonstrate their new guidelines. There's our secondary endpoints from the effect of omega-3 fish oil consumption on cardiac heart disease, stroke, or central cardiac and vascular diseases. Okay, and what you see here is the 17 endpoints, the original estimator in red, and the 95% confidence interval is the dotted red ones. Simultaneous overall possible selection means that from these 17, I can pick any one, and the confidence interval, which is now shown by this gray one here, that this confidence interval will still have the right coverage. It might be conservative, but it will have at least 5% error. If I choose a group of these, it will all live together, they will have it. So this is strong protection. Simultaneous over the selected, which we introduced recently, say, suppose I want only those that are very close to 1, the 5 ones that are close to 1, and I want to have simultaneous inference over these 5, then I can get a little bit better. Conditional on being selected is, suppose I use the rule that if the coverage, if the confidence interval doesn't cover 1, I choose this parameter and report it or highlight it in the abstract. Then I can create a confidence interval which is conditional on being selected, and this will be the blue ones. And you see that the blue ones here are even shorter in this direction from the original ones and are further away towards 0. And finally, I can have on the average over the selected, suppose I choose the 4 that are, that the 95 confidence interval doesn't cover 0. I want to have on the average over this, the right error rate. Note that on the average overall, this is the 95% interval does it. But once we select one of these, it's no longer a 95% confidence interval. It's the adjusted one that is. Now, a question was raised about what do we do in complicated situation, like analysis of variance. So here's an example taken, taken from the replicability, one of the studies in the replicability project, and it is representative of many of these, where you have various studies in the paper. And in this study, there were 3 unknown analysis of variance, 3-way analysis of variance. And then in each analysis of variance, there were both interaction, primary main factor comparison, and 3-way interaction. And in fact, one of them, I hope you can see it because a bit, one of them were used for replicability assessment, okay? How do we deal with something like that? Well, that's the recent theory that we developed, hierarchical one, in which we go down and test and compare. Here we have 3 tests with p-values. We do BH testing for this one. If only one passes, we go down in this direction using 1/3.05. But if all 3 of them are significant, we can go down at 3/3 times 0.05. That is, we can test this 8 at the 0.05 level. And if we further find here something and we want to go further down, then we will do accordingly. The more we select, the more we have to be careful. The less we select, the danger is less. Using this kind of methods on the 100 replicability problems, which is a project that PhD of Yoav Aviv and some other students of mine did, there was a transparency problem only in 1 of them. There were a reproducibility problem in 6 of them, where a declared 0.05 wasn't the 0.05. We ended up with 88. 56 of them failed, which is 64%, just like the original 100, which had 64% failure. There was evidence selection in each paper. There were between 7 and 720 inferences per paper. The average was 71. Okay, adjusting using this kind of method, hierarchical FTR, 22 with P adjusted bigger than 0.05 had to be screened out. Of them, 21 were non-replicable results, and we lost only one replicable discovery. So the failure rate decreased to 52%. It gave us an opportunity to check the proposal to simply reduce to P less than 0.005. That was discussed yesterday, Benjamini et al. Representation with 200 signatures. Then there were 32 with P bigger than 0.005. Of them, 21 non-replicable results, but 11 replicable discoveries. So the failure rate remained at 64%, and the power loss was a third. So the point is that true, multiple testing reduces the level at which you want, but it does it depending on the analysis that you are doing. About the statistical wars, I gave a previous talk about the statistical wars, and so the details in this forum, so the details can be found there. I'll just outline what happened. First of all, identifying the problems of non-evidence selective inference with the use of p-values and statistical testing. Well, that's not surprising. Everyone was using p-values and statistical testing. It ended with new statistics and Ben. So the second one was the ASA guidelines regarding the p-values, which ended with some statisticians prefer or even replace p-values with other approaches, such as Bayes factor, confidence interval, and so on and so forth. This was not a consensus report. I participated in this one, so did Philip Stark, who is in the audience. It was a report that had 20 disconcerning papers that didn't appear in the print version. There was the 2019 ISA conference and editorial with the title Scientific Methods for the 21st Century Award Beyond P less than 0.05, with an editorial by the same people who wrote the ASA guidelines. Don't use P less than 0.05, don't say statistically significant. And that vote Karen Carpenter, the ASA president, to create a task force, because the 2019 ASA editorial was identified as the second ASA one. And the task force said that p-values, Mayo mentioned it, p-values are valid statistical method. Indeed, p-values and significant testing are among the most studied, best understood statistical procedure. They are important tools that have advanced science to their proper application, but more important that we give 1 page of assessment of how this should be done regarding all them. For example, no single statistical summary can clarify the uncertainty in the conclusion. You need both p-values, confidence interval, estimator, standard deviation. You need both credence interval, Bayes factor, and so on and so forth. But by 2022, and this I didn't speak about, Don McNaughton filed 41 examples of papers that addressed the ASA editorial as an ASA policy. So she wrote a letter to the board of ASA. Either the board approves the editorial as policy or the disclaimer is added. Finally, after 3 years, a disclaimer was added, but only on the online version. But at least we can refer to that. It's not giving up statistical significance. It's not ASA policy, but the work goes on. Scientific reproducibility and statistical significance symposium that was convened on June 3. The goals of the symposium were to offer alternatives and to discuss changes to publication. It's not the end of it. My point is that the war between Bayes and frequentists was fierce in the 50s, but it receded to coexistence and mutual respect. And the replicability analysis crisis was used by zealous Bayesians to restart the war. And there was no reason for that. And unfortunately, I see no connection between stat wars and replicability. What are some of the casualties of the English Journal of Medicine guidelines? When p-values are reported for multiple outcomes without adjustment for multiplicity, the probability of declaring a treatment difference when none exists can be much higher than 5%. This is the new guidelines, but p-values may not be reported for secondary endpoints if multiplicity correction method wasn't specified in the protocol. And so only unadjusted 95 confidence interval should be reported for all secondary endpoints. That's also the open science directions. Well, what happens? I'll show you the example before. There were 4 confidence intervals that didn't cover 1. Here are the 4 confidence intervals. And one of them was discussed in the discussion section, and 4 of them were picked by another citing result just a few months later. The point is that 95% confidence interval offer themselves to selection. They are being selected. What is the problem with that? Well, first of all, CI as a decision tools, they are exactly like significant testing get a 0.05. So the issue of multiplicity as recognized by New England Journal of Medicine doesn't disappear. Second, there's a problem with confidence interval coverage. Okay, taking the 17 estimators from above as parameters and running a simulation, selecting the confidence intervals that do not cross 1, and checking what is the average non-coverage of the so selected, then you get 11%. And if you attenuate the estimators, not believing that they reflect the true ones, take half of them, then it's 18%. And if you put all of them close to 0, but none at 0, it's 50%. It simply deteriorates entirely. Okay, so we suggested actually, after discussing the issues with some of the statistical advisors of the English Journal of Medicine, we understood that they want a single, if anything, they want a single default measure, Okay, so a default measure is you select, if it is 95% interval doesn't cover 0, but then you enlarge the confidence interval to at least assure false coverage rate on the average over the selected. The second casualty was mentioned by Mayo yesterday. A student of mine discovered it. Persistence in getting null hypothesis significant essays removed from clinical papers I'm reviewing worked. After 3 rounds of revisions, all p-values have been removed from the study. The use of the term statistically significant has been removed from the manuscript. A question in Twitter. She has 13,000 followers, by the way. Sam Horowitz said, I'm going to guess that magically somehow the paper retains the same conclusion. Magically, you are correct. So I don't need the significance to tell me that 44% and 14% are different from one another. Now, any statistician would shudder from that, because if the sample sizes are even 15, this is not true. If the sample sizes are 100, this is true. I'll skip this too, because I want to get to the issue of how the 2 pillars are addressed in frequentist and Bayesian eyes. Addressing the relevant variability is quite ignored by many, but has increasing awareness. For instance, doctoral reviews now require to use random effects analysis rather than what is called common effect analysis in their
Yoav, your slides are not advancing.
But the insistence on actually a random sample of levels hinders back this application. Bayesian, it is recognized, interestingly. The hierarchical modeling tries to capture, in many cases, the structure. Gelman is arguing for that, but there is an effort in this direction. Addressing evidence selective inference is recognized by frequentists, more from p-values than for confidence interval, as I mentioned, and certainly not for exploratory research, which I disagree. If the exploratory research deals from many hypotheses, it should be controlled in some way. But Bayesian ignore it as a matter of principle. From Gelman and Gima paper, it carries the title, Why We Don't Have to Worry About Multiple Comparison. And the underlying theoretical justification is, since we condition on all the data, any selection after the data is viewed is also reflected in the posterior distribution. There is an example in Gelman's web. Assumes prior mu 0.5 standard deviation, 1 million, and the parameters generated from this one, and what we see, and then there is a noise added to each parameter, normal 0, 1. And what he argues that if you use marginal confidence intervals not covering the parameters is 5%, intervals not cover 0 are 7.3. But if you take out of them, 48% of them do not cover the parameter. But Bayesian credibility, they do wonders, okay? They choose less, only 0.01 of them are not selected, but only 3.4% of them. So I took this, by the way, marginal for confidence interval also do that. I took this example and just modified this prior with 0.001 normal 0, adding standard deviation of 3. Okay, so just perturbed in 1 in 1,000 the prior, and did it the same. Bayesian credibility intervals, 5.1% on the average. Well, that's not, I mean, it's okay on the average. 0.03 not covering, fine. But 71% of the credence interval did not cover their parameters. This has a second act to this. BH adjusted and confidence interval do what they're supposed to do and give 2.1%. Last month, from Gelman's blog, Eric van Zwet offers a solution for the above example. We can mix the normal 0 half
Yoav,
with any wider normal distribution with almost any probability, and then very large effects will hardly be shrunken. And he demonstrated it by this prior with 0.01 normal 6 power of the 741 credible intervals not covering 0, the proportion not covering parameter is 0.007. And so it's not that bad. And Gelman responds in their blog, I continue to think that Bayesian inference completely solves the multiple comparison problem. So I generated data from this prior, to which I added normal 4.05, so I will not put it very far away, and got 29% of those selected, not covering their parameters, with an order of magnitude power loss relative to frequentist FDR adjustment. So my point is that Bayesian should worry about selective inference if they care about replicability. They cannot hide behind puristic theoretical guarantees. And some Bayesian do that. There's connection between FDR and large inferential problem, Genovese and Wasserman story, effort works in empirical Bayes, and even purely Bayes models that were suggested by the Tukey and thresholding of posterior odds using BH. So some do, but the main course of Bayesian just do not agree to this. So I come to my takeaway messages. Replicability can be enhanced mainly by addressing selective inference and the relevant variability. Selective inference, many deal with non-evident, but evident selective inference is as harmful as non-evident selective inference. It is needed in exploratory research, even when the pool is small. So in genetics, they started to address multiplicity when the number of gene expression measured reached 6,000. In QTL analysis, when it reached 700. In experimental psychology, it's already there, but people ignore it. People simply ignore it. It is needed for confidence interval. You can't hide behind the statement that confidence intervals are better than p-values, and therefore, because they have more information, and therefore, you don't have to worry about multiple comparison. And finally, that A's attitude against p-value and statistical significance is political and is harmful to replicability. As to the relevant variability, prefer random effects even if it's not justified. In fact, Tukey even suggested to multiply what you estimate from the random effect by a factor bigger than 1 if you believe that your laboratories are too close to one another, which may bring some Bayesian structure to this statement, but prefer it to assuming that the variability relevant is the one you measure in your laboratory. Interestingly, Schuller came to the conclusion that he will always do experiments with his 3 friends after finding that his verbal shadowing effect really was vertebrate only after using this kind of structure. But in his later papers, it's difficult, it's not done that way. What we did is we used databases for that, and we didn't, I mean, as I told you, we didn't standardize strictly our experiments. It is better evidence for scientific knowledge if it is not standardized too much. And in this line, many small studies are better than one or few large ones, because if you do a random effect analysis, you gain from assessing the variability from many small studies. This goes against the usual notion that replicability studies have to be large. Okay? Scientific knowledge accumulates. And as I showed, if it accumulates too slow, as I showed in the tomato example, it's not the right way. What we have to do is try to reduce the replicability problem so it won't take 20 years to see that the result is wrong. Finally, most Bayesian ignore selective inference, but appreciate addressing relevant variability. For frequentists, it's the opposite, unfortunately. In both research communities, practitioners try to avoid addressing both issues. Until when? Until research complexity is so large that selective inference is addressed, or until results are so non-replicable by others in other countries that the relevant variability is addressed. And this simply usually takes too long. Thank you.